In this video, we're going to discuss how to fit unconditional hierarchical linear models using R. There will also be some materials posted on Blackboard that can show how to do this exact same procedure using SPSS and SAS, but because we're focusing on R in this class, that's going to be the focus of these slides. So for HLM and R, there isn't actually a built-in function. We need to use a package, and the package that we're going to use is LME4. So make sure that you install the LME4 package because we're going to use this a lot this semester. The core function that we're going to look at for fitting hierarchical linear models is the LMER function. And the basic syntax is very similar to the AOV and LM functions in that it is a formula syntax with the outcome variable on the left, then a tilde, then the variables all separated by pluses, and the data. The key difference between the LM and AOV functions and LMER is that we need to specify our ID variable or our random effects. And in this case, we do this with by adding an extra variable in the end, which in parentheses is one with a vertical bar and then our ID variable. In this case, the one represents that we are specifying random intercepts, or we're only interested in cluster means because we're doing an unconditional model, and this is only a random intercepts model. We'll look at models with random slopes where we replace the one with other variables later in the semester, but for now, don't worry too much about that. You just need to know that this extra piece of syntax is parentheses, one vertical bar, and then our ID variable. So we're going to use the pane data again. So this is the same data that we used earlier in the semester. So if you save the CSV with the column names, you can just load up the CSV. If not, you will need to load up the SPSS file and add the column names. So for specifying an unconditional model in HLM, this is what the syntax is going to look like. Here, P affect or positive affect is our outcome variable. So I'm going to name my model LMER underscore mod. That's just the object's name. You can name it pane mod or whatever you want. And then the syntax is LMER, P affect tilde, and because this is just an unconditional model with no predictor variables, we just have this specification for random intercepts with parentheses, with one vertical bar, person ID. And then finally, we specify our data at the end. To view our model results, we can call the summary on our model object. And you see you get a whole bunch of stuff here. You get a repetition of the model at the top. You get this convergence criteria. Don't worry too much about that right now. We'll talk about a little bit about what REML means a little bit more later in the semester, but this is essentially just confirming that the algorithm converged on a solution. And then you see these scaled residuals. Again, don't worry too much about that at the moment. What we're mostly worried about is going to be below that, and it's actually part of it's cut off, but we have the random effects and then the fixed effects. And let's zoom in a little bit on what these mean. So we can extract sigma squared mu and sigma squared epsilon, which are our random effects with the var core function. And you see those were printed in the summary function over here as well. But we can simply extract them by themselves with the var core function. And unfortunately, the var core function is going to only print out the standard deviation if you just call it by itself. If you want these in variance terms, which we often will, you have to call print around it, and then you have to tell it that you want variance with the comp argument. The comp argument can either be variance, standard deviation, or both. So the difference between variance and standard deviation, just again, is that standard deviation is the square root of variance. So here, because of this little exponent here, this is telling us that we want variances, and again, we often will want variances, so we call that here. And you see this, the way I called it, we get both the variance and the standard deviation. So this first row, where it says person ID and name intercept, this is sigma squared mu. This is the variance of the cluster means. And then the second row, residual, is the sigma squared epsilon. This is the remaining variance not accounted for by the cluster means. And then if we call the fixf function, we can get gamma 0, which is the mean of the cluster means. It's the population level cluster mean. So in SPS and SAS, you get an output for sigma squared mu with z-tests, and you won't get this with R. And the reason is that z-tests assume that standard errors are symmetric, and that's not really appropriate for testing variances. And so the people who wrote LME4 just decided we're not even going to give this to you the way some other software does. We could go through how to do it on your own, but it's not something you really ever need to or should do. We're going to talk about better methods instead. In this case, the better method for testing the significance of a variance is a likelihood ratio test. And you're going to talk more about what likelihood ratio tests are in the semester if you haven't looked at these before. But for now, all we need to know is that we can conduct a likelihood ratio test on sigma squared mu to test whether it is significantly different from zero, using the rand function from the Elmer test package. So you need to first install and load the Elmer test package, which is an extension of LME4. And then you call rand on your model, and you see you get an ANOVA-like table, which is actually doing a likelihood ratio test, and likelihood ratio tests are chi-square distributed. So in this case, we would say that our likelihood ratio test, which is here, is chi-square with degrees of freedom 1, is this value, which is really big chi-square. So this is telling us that our variance is significantly different from 0. We can also compute confidence intervals for our model for the sigma squared mu. So confidence intervals for the variance with the confident function. And this is also based on likelihood ratio methods rather than z-score methods. And again, the reason is this will give you asymmetrical confidence intervals, which is what we want for variances. We don't necessarily want, we don't at all want symmetrical confidence intervals. They're not appropriate. So one thing to note here is that what it's outputting is actually confidence intervals on the standard deviation. And you can note the standard deviation just by taking the exponent away. So this is just sigma mu 0. So that's sig 01. The top row is for the standard deviation of the cluster means, and dot sigma is for sigma epsilon, which is the residual variance or the residual standard deviation. And then intercept at the bottom is the confidence interval for the overall intercept, the population intercept. So to get this in variance terms, we can just square the confidence intervals. The problem is we don't want to square the confidence interval for gamma 0. That's the population mean. It's not a standard deviation term. That's just a mean. So squaring it is not what we're interested in. So we just want to specify that we want the random effects rather than the fixed effects. And we can do that with this extra argument, PARM for parameter equals theta underscore. That will just give you the sigmas. And then we can just square it, and that'll give us the confidence interval for our variances rather than standard deviations. So we've talked about doing significance tests for sigma squared mu, but more commonly what you're going to see is interclass correlation. You're not doing significance tests of the residual variance. You might see it here and there, but it's not super common. A lot of times you're just going to look at interclass correlation, which you can think of more of like an effect size. So it's conceptually, it's the proportion of variability that's attributable to the cluster means as opposed to the total variability in the data. So you could think of it, it's very similar to something like R square change, where you test the amount of variability accounted for by adding an additional variable and then comparing nested models. Or it's similar to ANOVA, where you're doing the sum of squares of an effect divided by sum of squares total, which would give you an eta squared effect size. So in this case, we're doing sigma squared mu divided by sigma squared mu plus sigma squared epsilon. And as a reminder, we can get these with the varchar argument, and we have to call print first to make sure we get variance rather than standard deviation. And then we can just plug in our numbers, and you should know how to do this by hand. It's fairly straightforward. So this goes there, this goes down here, and then this goes down here. So again, sigma squared mu divided by sigma squared mu plus sigma squared epsilon, and that gives us our interclass correlation. And while you should know how to do this by hand, there is a nice function that will do it for you. The ICC function, there's probably lots of different packages that have ICC functions. In this case, I'm using from the performance package. And if you call the ICC function on our model from the performance package, you see it gives us the same interclass correlation. In this case, it gives us an adjusted and a conditional version. They're the same here. Don't worry about that for now. And then finally, we can get the posterior cluster means of all of our variables if we want. And the way we would do this is we would use the ranf function. So this gives us the predicted cluster mean for each variable. Actually, what the ranf function is giving us is the difference from the population mean. So this is the actual mu0j's are differences from the overall intercept from the gamma 0 variable. So you have to add gamma 0 onto the mu0j's, and you can do that with this line of code down here. And this gives you the predicted cluster means for every cluster. So note, it's a little funky here because when I call mean diffs, it gives us this object that has sort of like a nested data structure. So you call mean diffs, then person ID from mean diffs, then intercept from person ID and mean diffs. So this is referencing the intercept term. And then for fixf, I put this 1 here because I only want the first fixed effect. There's only one fixed effect in this model, but we will look at models later in the semester which have additional fixed effects, which would include things like more predictor variables. But in this case, we just want the overall intercept, so I just stuck the 1 in there because if you want to use it later with other models, you'll need this. You won't actually need it here.